Have you ever wondered what lies beyond the stars? What if our universe was just a small piece of something much bigger? These questions take us on a journey to the limits of our knowledge. What secrets are hidden beyond our universe? Could there be more worlds out there beyond our wildest dreams? Join us in the search for answers and understand the greatest mysteries that exist. What lies beyond our solar system? The heliosphere is a vast, bubble-shaped region of space that encompasses our entire solar system. It is created by the solar wind, a stream of charged particles continuously emitted by the sun that pushes against the interstellar medium, the matter filling the space between the galaxy's stars. Within this bubble, the solar wind travels at high speeds, carrying with it the sun's magnetic field and forming a protective shield that deflects and modulates cosmic rays, which are high-energy particles from beyond our solar system, as it extends far beyond the orbit of the outer planets. The outer boundary of the outer heliosphere, marks the transition from the influence of the solar wind to the matter and forces that originate outside our solar system. Understanding the heliosphere is crucial for space exploration and for protecting satellites and astronauts from the harmful effects of cosmic radiation. Immediately beyond the heliosphere is the vast and mysterious expanse known as interstellar space. This is the region where the sun's influence diminishes and the solar wind, a stream of charged particles, is no longer dominant. Instead, the environment is characterized by the presence of interstellar matter comprising gas, dust, and cosmic rays from other stars and the galaxy itself. This transition marks a step from the relatively well-protected environment of the heliosphere to a space where cosmic rays are much more intense, and the chemical composition reflects the composition of the galaxy in general rather than that of our sun. The Voyager spacecraft, having crossed the pores of Helia, are now traveling through this unexplored territory, sending invaluable data that helps scientists understand the interaction between our solar system and the vast that extends beyond our solar neighborhood. Interstellar space is the vast and almost incomprehensibly extensive zone that lies between the stars within galaxies, extending far beyond the protective bubble of the heliosphere that envelopes our solar system. Unlike the heliosphere, dominated by the solar wind and the sun's magnetic field, interstellar space is filled with a thin soup of particles, mostly hydrogen and helium atoms, with traces of dust and cosmic rays. These cosmic rays, high-energy particles that travel through space at nearly the speed of light, originate from explosive events such as supernovas and interactions within a galaxy, providing a critical view of the processes that occur on a galactic scale. In this region, the density of matter is incredibly low, with only a few atoms per cubic centimeter, creating a cold and sparse environment that contains the clues to understanding the life cycle of stars, the formation of galaxies, and the composition of the universe beyond our local neighborhood. Delving into interstellar space represents one of humanity's greatest exploratory challenges, offering the possibility of discovering unknown phenomena that shape our galaxy. The detection of interstellar objects involves a combination of careful astronomical observation, cutting-edge technology, and a touch of serendipity, as these objects range from cosmic dust to more massive bodies, such as asteroids or comets. They enter our solar system at high speeds, with orbits distinct from solar system objects, revealing their origin beyond our local cosmic neighborhood. Astronomers use powerful telescopes with wide-field cameras to scan the sky for objects that move against the background stars. The unique trajectories and high speeds of these interstellar visitors distinguish them from objects orbiting the sun. Once a possible interstellar object is detected, follow-up observations become crucial. Scientists use various instruments to measure its trajectory, speed, size, and sometimes even its composition using spectroscopy, which analyzes the light that an object reflects or emits. This approach allowed the identification of Amamu, the first confirmed interstellar object to pass through our solar system, and I/Borisov, the first interstellar comet identified, demonstrating the combination of keen observation and the technological prowess needed to discover these messengers from the distant cosmos. The discoveries of Oumuamua and Borisov marked a watershed moment in astronomy, turning the theoretical concept of interstellar objects visiting our solar system into proven reality. Before the detection of Oumuamua in 2017, scientists had long speculated about objects from other star systems passing through ours, but had never observed one directly. Therefore, the discovery of Oumuamua was significant not only for its novelty, but as concrete evidence of the exchange of material between stars, offering a tangible connection to distant solar systems. Its unusual shape and acceleration patterns sparked intense study and debate, enriching our understanding of the variety and nature of celestial bodies. Following in its footsteps, the discovery of Borisov in 2019 was equally revolutionary, but for different reasons. As the first confirmed interstellar comet, Borisov provided astrophysicists with the opportunity to compare the composition of an object formed around another star with comets born in our solar system. Its observations suggested remarkable similarities that hint that the processes forming comets could be universal and extend throughout the galaxy. Together, Oumuamua and Borisov not only confirm the existence of interstellar travelers, but also open a window into the materials and conditions prevailing in other parts of our galaxy, offering clues about the formation and evolution of planetary systems, including ours. The closest star system to the Sun is the Alpha Centauri system, an intriguing set of stars joined by gravity and located just over 4 light-years from Earth. This stellar trio is composed of 2 Sun-like stars, Alpha Centauri A and Alpha Centauri B, which form a binary system, and a faint red dwarf, Proxima Centauri, which orbits the pair at a greater distance. Proxima Centauri, the closest of the 3 to our solar system, has captured it due to its proximity and the discovery of an Earth-sized exoplanet, Proxima b, which orbits within its habitable zone, the region where conditions could be suitable for liquid water to exist. The Alpha Centauri system serves as a cornerstone in the study of stellar and planetary systems, offering a relatively close view of how neighboring stars and potentially habitable planets can exist and evolve beyond our solar system. Its proximity makes it a priority target for future interstellar exploration, fueling dreams and scientific plans to one day send a spacecraft beyond our solar system to another star system. Astronomers measure the distance to stars using various methods, but parallax is one of the most fundamental and widely used techniques. Parallax is based on the apparent shift in the position of a nearby star relative to the background of distant stars. As the Earth orbits the Sun, imagine you extend your thumb and close one eye, and then switch eyes. Your thumb appears to move relative to the background, even though it is stationary. This is the principle of parallax. Astronomers measure the angle of this apparent shift from 2 points in Earth's orbit 6 months apart to calculate the star's distance. This technique is incredibly accurate for stars located within a few hundred light-years, but less so for distant ones, due to the smaller parallax angles presented by the more distant stars. Astronomers use more complex methods, such as standard candles, with a known luminosity of specific types of stars or celestial events is used to calculate distance based on their brightness from Earth. Through these methods, astronomers can map the distances and positions of the stars, which allows us to understand the vast scales of the universe. Red dwarfs are the most common type of star in the Milky Way galaxy. They are small and cold by stellar standards, with masses ranging from 75% to 50% of the Sun's and significantly lower surface temperatures, giving them their characteristic reddish hue. Despite their ubiquity, they are faint and difficult to observe directly, though they are immensely significant for several reasons. First, their longevity is astonishing. Red dwarfs burn their hydrogen fuel very slowly, giving them a lifespan that can span trillions of years, far exceeding stars like our Sun. This longevity provides a stable environment that could be conducive to the development and maintenance of life on planets orbiting them. In addition, due to their prevalence, many of the exoplanets discovered orbit these stars, including some within habitable zones where conditions could allow for the existence of liquid water. However, red dwarfs can show volatile behavior early in their lives, with powerful eruptions that could strip the atmosphere from planets orbiting nearby. Understanding these stars and the planets that orbit around them is crucial for astrophysics and the search for life beyond our solar system, which makes red dwarfs a central element in the field of astronomy. Red dwarfs can, in fact, harbor habitable planets, making them intriguing targets in the search for life beyond our solar system. The planets within the habitable zone of a red dwarf, where temperatures could allow the existence of liquid water on its surface, present a tempting possibility of habitability despite their potential. There are unique challenges associated with red dwarfs that could affect the habitability of the planets that orbit around them. One significant obstacle is the high level of stellar activity in red dwarfs, especially when young, including intense stellar flares and radiation that could strip a planet's atmosphere or make its surface uninhabitable for life as we know it. In addition, because red dwarfs are cooler and dimmer than stars like our Sun, their habitable zones are much closer to the star, which could lead to a tidal lock where one side of the planet is constantly facing the star, which creates extreme temperature differences across the planet's surface. Despite these challenges, the discovery of exoplanets in the habitable zones of red dwarfs, such as Proxima b around Proxima Centauri, fuels ongoing research about the possibility of life on these alien worlds. The durability and ubiquitous nature of red dwarfs means that if such planets can truly sustain life, they could be among the most common places in the galaxy. From the Proxima Centauri system, we have obtained valuable information about the characteristics and potential habitability of exoplanets orbiting red dwarfs, as well as about the dynamics of stellar systems different from our own. Proxima Centauri is the closest known star to the Sun. It houses at least 2 planets, Proxima b, located within the star's habitable zone, and Proxima c, a more distant gas giant. Proxima b, in particular, has captivated scientists and the public as a candidate to harbor conditions suitable for life. Its discovery highlighted the possibility that Earth-sized planets in habitable zones are more common than previously thought, even around the abundant ones in our galaxy. The study of Proxima Centauri and its planets has reinforced the idea that high levels of stellar activity and magnetic flares from red dwarfs could pose significant challenges to habitability, as they could strip atmospheres and expose orbiting bodies to intense radiation. However, these observations also open new avenues of research on how planets could protect themselves from such hostile conditions, for example, through strong magnetic fields or dense atmospheres, and how life could adapt to environments very different from Earth. It is important to note that the Proxima Centauri system serves as a nearby laboratory to test technologies and methodologies to detect and study exoplanets and assess their atmospheres and potential biosignatures in the search for extraterrestrial life. Binary and trinary star systems represent a deviation from the solitary sun of our solar system, offering a glimpse into the dynamic and varied nature of celestial encounters. In a binary system, 2 stars orbit around a common center of mass, influenced by each other's gravitational attraction. Triple star systems add another layer of complexity, with 3 stars involved in a gravitational dance that can take various forms. A close binary pair. Close binary pair with a distant third companion, or all 3 stars in a closer orbit, affecting each other more directly. The presence of multiple stars within these systems has a profound impact on the dynamics, formation, and stability of planets. For example, the gravitational forces in a closely bound binary or trinary system could alter planetary orbits, making it difficult for planets to maintain stable orbits, especially in tight configurations where the stars are very close. However, there are stable zones, usually far from the center of mass or at specific points where gravitational forces balance. This complexity adds intriguing possibilities for habitability and the types of worlds that could exist with planets that would experience drastic variations in light and temperature. depending on their orbit, compared to the relatively stable and predictable conditions of our solar system. Binary and trinary systems introduce a realm in which day and night cycles, seasons, and climate could be very different, assuming planets can form and persist in these environments. The study of these systems challenges our understanding of the formation and habitability of planets and offers the tantalizing prospect of discovering exoplanets in environments very different from our own solar neighborhood. An exoplanet, or extrasolar planet, is a planet that orbits a star outside our solar system. These distant worlds vary widely in size, composition, and orbit, and embody a diversity beyond what we see in our solar neighborhood. The discovery of the first exoplanets in the early 1990s marked a monumental shift in astronomy and expanded our understanding of the universe and the potential for life beyond Earth. Since then, thousands of exoplanets have been identified using various detection methods, such as the transit method, which observes the dimming of a star's light as a planet passes in front of it, and the radial velocity method, which detects the wobble of a star caused by the gravitational pull of an orbiting planet. Exoplanets provide a rich laboratory for studying planetary formation, structure, atmosphere, and potential habitability. They have been found in a wide range of environments, from very compact systems in which planets orbit their stars in a matter of days, to cold, distant worlds, and even rogue planets that roam the galaxy without a host star. Some exoplanets reside in the habitable zones of their stars, where conditions could allow liquid water, a crucial ingredient for life as we know it. The ongoing search and study of exoplanets not only deepens our understanding of the physical and chemical processes of planets, but also drives the age-old question of whether we are alone in the universe. Astronomers detect exoplanets through various ingenious methods, each of which takes advantage of the interactions between stars and their planets. One of the most successful techniques is the transit method, which monitors the light of a star for a periodic dimming caused by an orbiting planet passing in front of it, blocking a fraction of the starlight. This method not only confirms the presence of an exoplanet, but can also provide information about the planet's size and orbital period. Another main technique is the radial velocity method, sometimes called Doppler spectroscopy. Here, astronomers observe the slight gravitational pull that a planet exerts on its host star, causing the star to wobble. This oscillation slightly shifts the colors of starlight, moving toward the blue end of the spectrum as it approaches and toward the red as it recedes. By measuring these displacements, scientists can deduce the presence of a planet, its mass, and aspects of its orbit. In addition, the obtaining of direct images, which consists of taking real photographs of the planets and the gravitational microlens, which detects planets through the curvature of the light of a distant star when a planet passes in front of it, are other methods, although less used due to the current technological limitations. Each method has its strengths and weaknesses, and often they're used in combination to confirm the existence of an exoplanet and collect as much information as possible about its characteristics. Through these techniques, astronomers have unveiled thousands of exoplanets, enriching our understanding of the immensity and the diversity of the universe. The habitable zone, often called the Goldilocks zone, is a term used in astronomy to describe the range around a star where conditions may be suitable for life as we know it. This range is neither too hot nor too cold, which allows liquid water, a critical ingredient for life on Earth, to exist on the surface of a planet. The location of the habitable zone varies from star to star, depending on the size and temperature of the star. For our solar system, the Sun's habitable zone extends from slightly beyond Venus to about halfway through the orbit of Mars. Interestingly, as we expand our understanding of what makes a planet habitable, scientists now consider factors beyond temperature and water, such as a planet's atmosphere and magnetic field, to assess its potential for harboring life. This ongoing research continually shapes our search for life beyond Earth, making the concept of the habitable zone a fundamental piece in the cosmic puzzle of finding other worlds where life can thrive among the vast and varied expanse of the cosmos. astronomers have discovered some truly strange worlds that challenge our Earth-centered notions of what planets can be. For example, there's HD 189733b, known as the Blue Planet, not for its vast oceans like Earth, but for its deadly atmospheric conditions. This gas giant, located 63 light-years away, experiences winds so extreme that it rains glass in its atmosphere. Then there is Trace 2b, the darkest planet known so far, which reflects less than 1% of the light that hits it, making it blacker than coal. Interestingly, its surface temperature can exceed 1,000 degrees Celsius. Gliese 436b, a planet composed mainly of burning ice, presents another enigma despite its proximity to its star, which would normally vaporize the ice. The intense pressure keeps the water in a solid state, a phenomenon known as hot ice. These discoveries not only challenge our understanding, but also expand the range of possibilities about the forms that worlds can take in the universe, painting a picture of diversity beyond our imagination. Super-Earths represent a fascinating class of exoplanets that offer a compelling vision of the diversity of planetary bodies beyond our solar system. As their name suggests, they are planets larger than Earth but smaller than gas giants like Neptune and Uranus, with a mass usually ranging between 1 and 10 times that of Earth. Their size suggests that they could have stronger gravity, which could significantly affect everything from a planet's atmosphere to the behavior of liquids and gases on its surface. Despite the word Earth in their name, these planets may not resemble Earth at all. Some super-Earths could have dense and thick atmospheres, making them more like mini Neptunes than our home planet. Others could be rocky planets with vast oceans or completely dry land masses. The composition and conditions of these planets vary widely, reflecting a broad variety of environments. Interestingly, the presence of super-Earths in the habitable zones of their stars raises fascinating debates about their potential to harbor life. However, the existence and sustainability of life on such planets would depend on numerous factors, including atmospheric composition, surface conditions, and magnetic fields, among others. The discovery and continuous study of super-Earths continue to expand the limits of our understanding of planetary science, offering new perspectives on the complex tapestry of celestial bodies that populate our universe. Analyzing the atmospheres of exoplanets, worlds that orbit stars beyond our solar system, is a task that requires precision and innovation, given the enormous distances and weak signals involved. Scientists employ several ingenious techniques to observe these distant atmospheres. A widely used method is transit spectroscopy. When a planet passes in front of its host star, a small fraction of the star's light is filtered through the planet's atmosphere. Different gases in the atmosphere absorb different wavelengths of light, leaving revealing footprints in the light that reaches Earth. By studying these changes, astronomers can determine the composition of a planet's atmosphere. Another technique is direct imaging, which consists of taking actual photographs of the planets. This method is difficult due to the brightness of the stars, which eclipse the planets, but with advanced instruments, scientists can block the light of the stars to capture images of the planets. These images can then be analyzed to study the atmospheres. In addition, the technique of emission spectroscopy observes the light emitted by the planet itself, which provides information about its temperature and atmospheric composition. These methods and the data they provide are vital to understanding not only the atmospheres of these exotic worlds, but also to assessing their potential for habitability and the presence of life beyond Earth. A nebula is an impressive testament to the cosmic ballet of creation and destruction that characterizes our universe. It is essentially a vast cloud of gas and dust in space that serves both as a cradle for newborn stars and as a graveyard for the remains of those that have reached the end of their lives. Nebulae have diverse shapes and sizes, and each tells a unique story of cosmic phenomena. For example, emission nebulae shine distinctively when illuminated by the ultraviolet light of nearby hot stars, and their colors reveal the types of gases present, mainly hydrogen, which glows red. Reflection nebulae, on the other hand, do not emit their own light, but reflect the light of nearby stars, often showing a beautiful blue tone due to the scattering of light by dust. Dark nebulae appear as opaque silhouettes against the brighter background of space, with their dense dust clouds obscuring the light from stars or nebulae behind them. Finally, planetary nebulae mark the final stage in the life of medium-sized stars, which lose their outer layers, creating a bright layer of gas around the remaining core. The intertwined cycles of the birth and death of stars within these cosmic wonders not only contribute to the majestic beauty of the galaxy, but also play a fundamental role in the cosmic recycling of matter, providing the building blocks for future stars and planets. Stars are born in the densest regions of nebulae, where colossal clouds of gas and dust come together under the force of their own gravity. This process begins in the cold and dark pockets of nebulae, where the attraction of gravity causes gas and dust to clump together. As more material accumulates, the gravitational force at the center of the clump becomes stronger, attracting even more gas and dust. This increasing mass in the core causes an increase in pressure and temperature. When the temperature of the core reaches about 10 million degrees Celsius, nuclear fusion begins. This is the process by which hydrogen atoms fuse to form helium, releasing enormous amounts of energy, light, and heat. This marks the birth of a new star. As the newly born star continues accumulating mass, its gravitational influence of a newly born star can cause the collapse of nearby regions of the nebula, triggering a chain reaction of stellar births. The intense radiation from these new stars can also push outward the surrounding gas and dust, revealing the bright cluster of young stars. This dynamic process shows the life cycle of stars, from their dusty beginnings in nebulas to their appearance as bright orbs that illuminate the cosmos. The cosmos is adorned with a variety of nebulas. Each type offers a unique vision of stellar birth, life, and death. The emission nebulas, perhaps the most vibrant, are clouds of ionized gas that shine brightly due to the energy emitted by nearby hot stars. These colors, often in red and pink tones, result from the recombination of electrons with protons to form hydrogen atoms, a process that emits light. The reflection nebulas, in comparison, shine by reflecting the light from nearby stars. They usually appear blue because blue light scatters more easily than red, a phenomenon that is also responsible for the blue color of the Earth's sky. Dark nebulas, on the other hand, are dense clouds of dust and gas that obscure the light of objects behind them, appearing as shadowy figures against the brighter background of the Milky Way or other emission nebulas. Planetary nebulas present a different spectacle. They're the remains of dying stars that have expelled their outer layers, leaving behind a hot core that illuminates the expelled gas. Finally, supernova remnants are formed from the catastrophic explosion of a star in a supernova that scatters the outer layers of the old star into space. Each of these types of nebulas shows the intricate and varied processes that take place in our universe, from the formation of new stars to the remains left after a star's death. The Orion Nebula, a region of incredibly luminous and vast gas and dust, plays a crucial role in the study and understanding of stellar formation. Located about 1350 light-years away in the constellation of Orion, this nebula is one of the closest and most studied stellar formation regions. It serves as an astronomical laboratory, providing scientists with invaluable information about stellar birth processes. The nebula is full of a rich tapestry of protoplanetary stars, protoplanetary disks, precursors to planetary systems, and dynamic gas movements within the Orion Nebula. The intense ultraviolet light from the most massive and hot young stars ionizes the surrounding gas, causing it to shine and offering a spectacular view. In addition, the dense molecular clouds of the nebula contain the raw material, hydrogen, helium, and dust, that collapses under gravity to form new stars. This continuous stellar formation activity makes the Orion Nebula a vital area of study for astronomers seeking to understand not only how individual stars are born, but also how they influence their natal environment and the formation of planetary systems. Through observations of the Orion Nebula, researchers can reconstruct the complex interaction of forces that govern stellar formation, shedding light on the life cycle of stars throughout the cosmos. Observations of nebulas offer a window into the chemical and physical processes that sustain the composition of the universe. By analyzing the light emitted or absorbed by these vast clouds of gas and dust, astronomers can identify the elements present in their abundance. This technique, known as spectroscopy, reveals the distinctive signatures of different elements and molecules, such as hydrogen, helium, carbon, and oxygen. Since nebulas are the birthplace of stars, understanding their composition provides information about the raw materials from which stars and planetary systems form. In addition, the distribution and density of elements within nebulas inform theories about the origin of the universe and the life cycle of stars. For example, the heavier elements found in nebulas are often the remains of supernovas, the explosive deaths of massive stars. These observations support the idea that the heaviest elements in the universe were forged in the heart of stars and spread through space by supernova explosions. Consequently, by studying the nebulas, astronomers reconstruct the cosmic puzzle of how stars evolve, enrich the interstellar medium, and contribute to the complex chemical composition of galaxies. This, in turn, provides a broader understanding of the composition of the universe and the evolutionary processes that shape it. The Agila Nebula, home to the emblematic pillars de la creation, has been a spectacular source of discoveries and information about stellar formation processes. The pillars de la creation, columns of gas and dust that rise, have revealed invaluable information about how stars are born from dense molecular clouds. Observations made with the Hubble Space Telescope in the mid-1990s and, more recently, with advanced instruments, have shown that these pillar-shaped structures are incubators of new stars. The ultraviolet light from nearby massive young stars is sculpting the pillars, evaporating the gas and dust, but also triggering the collapse of the densest regions within the pillars to form new protostars. What has particularly fascinated astronomers is the dual role of massive stars. Their radiation helps form new stars by compressing gas and dust, but can also destroy the nurseries in which they form. The detailed images and data from the Agila Nebula have helped refine the theoretical models of stellar formation, showing how stars can emerge from turbulent and dense interstellar clouds. In addition, the observations of the Agila Nebula have underscored the importance of understanding the life cycle of interstellar matter, from dust to nebula and back to dust enriched with heavier elements forged in stellar furnaces. This cycle is vital for the cosmic evolution of galaxies, including the development of planetary systems that could harbor life. Therefore, the Agila Nebula and the pillars de la creation serve as a microcosm of the broader universe, illustrating the ongoing processes of birth, transformation, and renewal that define the cosmos. A star leaves the main sequence, marking the end of its stable hydrogen combustion phase due to the depletion of hydrogen fuel in its core during the main sequence phase. A star fuses hydrogen into helium in its core, a process that produces the energy needed to counteract the force of gravity that pushes the star inward. This delicate balance maintains the stability of the star for millions or billions of years, depending on its initial mass. However, as the hydrogen in the core is consumed, the fusion process slows, leading to a decrease in energy production. This causes the core to contract under gravity, which in turn increases the temperature and pressure of the core. In stars like the Sun, once the hydrogen in the core is substantially depleted, the increase in temperature and pressure allows the fusion of helium into heavier elements such as carbon and oxygen, marking stellar evolution out of the main sequence towards its next life stages, which for Sun-like stars include the red giant phase and, in more massive stars, the core contracts more dramatically and reaches even higher temperatures, allowing the fusion of even heavier elements, leading them through different evolutionary paths that may include stages such as the massive. The core contracts more drastically and reaches even higher temperatures, allowing the fusion of even heavier elements, leading them through different evolutionary paths that may include stages such as the supergiant, the supernova, and, Ultimately, a neutron star or a black hole. The transition from a main sequence is, therefore, a crucial moment in the life of a star that determines its future. The evolution and eventual return of enriched material to the interstellar medium contributes to the cycle of star formation. A white dwarf represents the final evolutionary state of stars that are not massive enough to become neutron stars or black holes, typically those with initial masses up to 8 to 10 times that of our Sun. These stellar remains are what is left after a star has exhausted its nuclear fuel and expelled its outer layers, leaving behind a dense core that cools. They are incredibly dense objects with a mass comparable to that of the Sun, but compressed into a volume similar to that of the Earth, which gives rise to a gravity 1,000,000 times stronger than that of the surface of the Earth. White dwarfs are mainly composed of degenerate electron matter, meaning that the electrons are packed as tightly as quantum mechanics allows. This creates a state in which no further compression can occur, allowing the white dwarf to resist the crushing of its own gravity despite the lack of internal nuclear fusion to counteract it. The lack of fusion means that a white dwarf does not generate new heat, so it radiates residual heat slowly over billions of years, going from white to red, and eventually becoming a cold and dark black dwarf, a theoretical endpoint that the universe is not yet old enough to have produced. The study of white dwarfs provides astronomers with key knowledge about stellar physics, the life cycle of stars, and the future of solar systems. Their constant cooling serves as a cosmic clock that helps measure the age of surrounding star clusters. In addition, the compositions of the planets and asteroids that once orbited the star and have since fallen into the white dwarf can be detected in its atmosphere, offering a unique window into the evolution of the planetary system. Long after the star's apogee, a supernova occurs as the cataclysmic end of a star's life, an event so luminous that it can briefly eclipse entire galaxies. This stellar explosion can occur in two main ways linked to the life cycles of different stars. In the case of a massive star at least 8 times the mass of the Sun, a supernova occurs when the star has exhausted its nuclear fuel and can no longer sustain the fusion process that balances the force of gravity. The core collapses under its own weight, heats up immensely, and, until it finally implodes, causes the outer layers of the star to explode outward. This type of supernova is known as a core collapse supernova. The second type, a Type I supernova, occurs in a binary star system, where one star is a white dwarf. The white dwarf accumulates matter from its companion star, increasing its mass until it reaches a critical limit known as the Chandrasekhar limit, which is approximately 14 times the mass of the Sun. At this point, the white dwarf undergoes a runaway nuclear fusion reaction that leads to its spectacular destruction. Both types of supernovae are vitally important in the cosmos, as they disperse elements such as carbon, oxygen, and iron into the interstellar medium, which will become the basic components of new stars, planets, and ultimately, life itself. In addition, the shock waves from supernovae can trigger the formation of new stars in nearby clouds of gas and dust. The study of these explosive events helps astronomers understand the life cycles of stars, the chemical evolution of galaxies, and the distribution of elements throughout the universe. A neutron star is an extraordinary celestial object that marks the collapsed core of a massive star after it has undergone a supernova explosion. When a star with at least 8 times the mass of the Sun exhausts its nuclear fuel, the outward pressure from the fusion reaction ceases, causing the star's core to collapse under its immense gravity. This collapse occurs so rapidly and strongly that protons and electrons are compressed to form neutrons, resulting in a neutron star. These stars are among the densest objects in the universe. Only an amount of material from a neutron star the size of a sugar cube would weigh about 1 billion tons on Earth. Neutron stars typically have a radius of only about 10 kilometers, but possess a mass between 14 and 216 times that of the Sun, demonstrating their incredible density. Their surfaces are extraordinarily hot, with temperatures reaching up to 1,000,000 degrees, and rotate at astonishing speeds, sometimes several hundred times per second, due to the conservation of angular momentum from the parent star. Many neutron stars are observed as pulsars that emit beams of electromagnetic radiation from their magnetic poles as the neutron star rotates. These beams sweep through space like lighthouses, and if they intersect Earth, they can be detected as regular pulses of radiation that can be observed with radio telescopes. The study of neutron stars not only sheds light on the life cycles of massive stars and extreme states of matter, but also provides a natural laboratory for understanding the fundamental laws of physics under conditions unattainable on Earth. These remnants of supernova explosions expand the limits of our knowledge about matter, gravity, and the universe itself. Predicting the exact moment when a star will become a supernova remains one of the most important challenges in astrophysics. Although scientists understand the general conditions in which a star ends its life in a supernova explosion, predicting when that event will occur in the life cycle of a particular star is notoriously difficult. The process leading to a supernova involves complex physics operating on timescales ranging from millions to billions of years, making it difficult to determine the timing precisely. For massive stars, astronomers can identify candidates likely to become supernovae based on their mass, age, and stage in the stellar life cycle. These stars show signs of approaching the end, such as the synthesis of heavy elements and increased instability. However, in physical terms, imminent can still mean thousands or hundreds of thousands of years. Type I supernovae, which involve white dwarfs and binary systems, also resist precise prediction. Astronomers can determine systems in which conditions appear ripe for a supernova, in which the white dwarf is approaching the critical mass limit after stealing matter from its companion, but the timing of the inflection point remains difficult to determine. Despite these challenges, advances in observational techniques, theoretical models, and computational simulations are improving our understanding of supernova precursors, although we still cannot predict their appearance with great precision. The study of candidate stars and the enrichment of our understanding of stellar evolution provide invaluable knowledge to the field, gradually bringing us closer to predicting these cosmic fireworks. Black holes, those enigmatic cosmic anomalies, are essentially regions of space where the pull of gravity is so intense that nothing, not even light, can escape its grip. Imagine the universe as a vast fabric of space-time, with massive objects like stars and planets creating dimples in this fabric due to their gravity. Now, a black hole does more than create a dimple. It is like a puncture that penetrates deeply into the very fabric of space and time. The boundary around a black hole beyond which nothing can return is called the event horizon. It is like the point of no return. When massive stars much larger than our Sun exhaust their nuclear fuel, they can undergo a catastrophic collapse that leads to the birth of a black hole. Within the event horizon lies the singularity, a point at which all matter is believed to be infinitely dense and the laws of physics, as we know them, cease to function. Despite their name, black holes are not empty, but rather large amounts of matter compressed into a very small area. The idea of something so powerful that not even light can escape, it may seem like science fiction, but it is a reality confirmed by numerous observations and technological advancement. The study of black holes unites the realms of theoretical physics and the observable universe, offering tantalizing clues about the very structure of our cosmos. Detecting black holes, given their nature of absorbing all light, may seem like an impossible task at first. However, scientists have devised ingenious methods to observe these cosmic enigmas indirectly by observing the effects they have on their environment. One of the main ways to detect a black hole is through the observation of X-ray emissions. When a star gets too close to a black hole, the intense gravitational attraction of the black hole begins to strip the star of its outer layers. This material spirals into the black hole, heating up to millions of degrees and emitting high-energy X-rays in the process. These X-rays are detectable by satellites and observatories located outside Earth's atmosphere, which is opaque to X-rays. Another method involves observing the gravitational effects of black holes on nearby stars. In some cases, black holes have companion stars in a close orbit around them. The gravitational influence of the black hole causes observable changes in the companion star's orbit. By studying these changes, astronomers can infer the presence of a black hole and estimate its mass. The great advance in observing the effects of black holes on spacetime itself came with the detection of gravitational waves, undulations in the fabric of spacetime caused by massive objects that move with acceleration. These waves were predicted by Einstein's theory of general relativity and have been observed from collisions and mergers of black holes billions of light years away. Each of these methods provides a unique window into the study of black holes and the extreme conditions that prevail in their environment, offering information on some of the deepest questions of physics and cosmology. The Via Lactea, our galaxy, is a vast island of stars, gas, and dust with a structure that captivates the imagination of scientists and astronomers. Imagine it as a gigantic spiral with long arms that wind around a bright and bustling center, much like the pattern of a cosmic swirl. At the heart of this spiral structure lies the galactic nucleus, a densely populated region that burns with the light of millions of ancient stars. This nucleus is enveloped by the bulge, a spherical zone full of stars, some of which are among the oldest in our galaxy. Radiating from the central bulge are the spiral arms, regions rich in gas and dust and dotted with brighter, younger stars. Our solar system is located in one of these spiral arms known as the Arm of Orion, about 27,000 light-years from the galactic center. Surrounding the disk of the galaxy, where the spiral arms reside, is the halo, a spherical cloud of older stars and globular clusters orbiting the galactic nucleus. Invisible to the naked eye, but detectable by astronomers, is the vast halo of dark matter enveloping the Via Lactea, exerting a gravitational force that prevents the galaxy from disintegrating. As it rotates, the Via Lactea is part of a local group of galaxies and is approaching the Andromeda Galaxy, with which it is expected to merge in about 4 billion years. This intricate structure of the Via Lactea, composed of the bulge, the disk, the arms, and the halo, is more than an impressive backdrop for our night skies. It tells the story of the evolution of our galaxy and, by extension, the cosmos. Measuring the size of the Via Lactea, our galactic home, poses a unique challenge, mainly because we reside within it. It is like trying to map a forest from within the trees. However, astronomers have developed methods to reconstruct this cosmic puzzle. A key approach is to study the distribution and movements of stars, globular clusters, spherical collections of stars that orbit the galactic nucleus, and gas clouds within the Via Lactea. By observing the orbits of objects in the outer regions of the galaxy, scientists can estimate the mass of the Via Lactea, which in turn gives clues about its size. Another method is based on measuring the distances to various objects within the galaxy using a technique known as parallax, which involves observing an object from two different positions in the Earth's orbit around the Sun to calculate its distance based on the apparent changes in position. By mapping the distances to stars and nebulae in different parts of the galaxy, astronomers can outline the structure and extent of our galaxy's spiral arms and other features. Advances in telescopes and detection methods, such as radio astronomy, allow scientists to probe the dark, dust-filled regions of the Via Lactea that are not visible in optical light, providing a more complete picture of the size and shape of the galaxy. Recent studies combining observations of the positions of the stars, their movements, and the gravitational attraction of the galaxy suggest that the Via Lactea extends to about 100,000 light-years across and contains several hundred billion stars. This ongoing search to measure the Via Lactea not only deepens our understanding of our cosmic environment, but also helps astronomers refine the techniques used to explore galaxies beyond our own. At the heart of the Via Lactea lies a region that has long intrigued astronomers and astrophysicists, the galactic center. The focal point of this bustling center is an object known as Sagittario Asterisco, pronounced Sagittario AR, a supermassive black hole that weighs approximately 4 million times the mass of our Sun. Despite its colossal mass, Sagittario Asterisco is relatively quiet compared to other galactic centers, as it emits only sporadic bursts of energy when interacting with its environment. The environment surrounding Sagittario, a asterisco, is a dense and dynamic mixture of various celestial objects, including clusters of stars that move at high speeds and immense clouds of gas that stir under the influence of intense gravitational forces and remnants of stars that have reached the end of their lives. These stars orbit the supermassive black hole at such high speeds that their movements have allowed astronomers to measure the mass of Sagittario, an asterisco, with remarkable precision. The discovery of this supermassive black hole and the study of its characteristics have provided crucial information about the nature of galactic centers and the role of black holes in the formation and evolution of galaxies. The detection of Sagittario, a asterisco, and its properties was achieved primarily through radio and infrared observations, which can penetrate the dense clouds of dust that obscure the galactic center for view. This area, invisible to light, remains a priority target for observations across the electromagnetic spectrum, as scientists strive to understand the complex interactions between the supermassive black hole and its galactic neighborhood. The center of the Via Láctea, with Sagittario, a asterisco at its core, is therefore not just a point in space, but a vibrant laboratory for studying the forces that shape galaxies across the universe in the great cosmic dance of the Via Láctea. Stars orbit the galactic center in much the same way that planets orbit a sun, but on a much larger and more complex scale. The force that dictates these orbits is gravity, exerted predominantly by the colossal mass concentrated in the center of the galaxy, including the supermassive black hole, Sagittario, an asterisco, and the dense bulge of stars that surrounds it. However, unlike the relatively circular orbits of the planets in the solar system, the stars in the galaxy follow orbits that are often elongated, taking them through various parts of the Via Láctea's disk and, for some, to the more sparsely populated halo surrounding the galaxy. The stars closest to the galactic center orbit faster due to the greater gravitational attraction they experience, completing a circuit in a few 100 million years. Those further away, like our Sun, take longer, with the Sun's orbit around the center of the Via Láctea estimated at about 250 million years, a journey that it has made about 20 times since it formed 46 billion years ago. The specific characteristics of a star's orbit depend on its initial position and velocity within the galaxy, resulting in a wide variety of orbital paths. In addition, the disk of the Via Láctea is not a flat and static structure, but a dynamic environment with spiral arms that contain higher concentrations of gas, dust, and young stars. These regions can slightly disrupt the orbits of stars as they pass through or near them, adding to the complexity of stellar motion. Understanding these orbits and the distribution of stars within the galaxy provides invaluable information about the formation and structure of the Via Láctea and the gravitational forces acting within it. Dark matter is a mysterious and invisible form of matter that does not emit, absorb, or reflect light, making it completely undetectable by electromagnetic methods. Despite being invisible, dark matter is believed to make up about 85% of the total matter in the universe. Its presence is deduced from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. In galaxies like the Via Láctea, dark matter plays a crucial role in shaping their structure and evolution. It forms a vast halo that envelopes galaxies and extends far beyond the visible boundaries defined by stars and gas. The gravitational attraction of this halo of dark matter keeps the galaxies together, influencing the orbits of the stars that are inside it. Without dark matter, the rotation speeds of the stars at the edges of the galaxies would be much slower than what is observed given the amount of visible matter. In fact, the rotation curves of the galaxies, which show the speed of the stars at various distances from the galactic center, provided some of the first evidence of the existence of dark matter. In addition, dark matter affects the formation and grouping of galaxies throughout the universe, acting as a cosmic scaffolding on which galaxies build in the early universe. The slight excessive densities of dark matter attracted nearby gas and dust, which led to the formation of galaxies and clusters in regions with higher concentrations of dark matter. Therefore, understanding dark matter and its properties is essential to study the formation, structure, and future evolution of our galaxy and the universe as a whole. Despite its elusive nature, ongoing research and innovative detection methods continue to unravel the mysteries of dark matter and its fundamental role in the cosmic ballet. The future of the Via Lactea is destined for an amazing transformation, courtesy of celestial mechanics and the relentless attraction of gravity over billions of years. Our galaxy, along with its vast set of stars, gas, and dark matter, is on a collision course with its largest neighbor, the galaxy of Andromeda. This monumental event, which is predicted to occur in about 4,000 million years, marks a key chapter in the future of the Via Lactea. As Andromeda and the Milky Way approach under the inexorable force of gravity, the initial stages of their interaction will distort their spiral structures, launching stars into new orbits and triggering new waves of star formation as gases compress in regions. Despite the dramatic nature of this galactic fusion, the enormous distances between stars make it unlikely that direct collisions between them will occur. Instead, the two galaxies will gradually merge into a single larger galaxy over billions of years, a process accompanied by spectacular cosmic fireworks as new stars are born. The new galaxy, sometimes, to which in astronomical circles is whimsically referred to as Mila or milk dromedary, is expected to be of a different type compared to its progenitors, probably an elliptical galaxy, which is more rounded in shape, due to the more random orbits of its stars. This transformation will also see changes in the night sky, with new star patterns emerging over millennia. In addition, the fate of the solar system in this great event is uncertain, although it is likely to be launched into a new orbit around the center of the newly formed galaxy. There is a small chance that it will be expelled into intergalactic space or find a new home orbiting a different galaxy. Regardless of the details, the fusion of the Via Lactea with Andromeda underlines the dynamic and ever-changing nature of the universe, a testament to the cosmic cycles of birth, transformation, and renewal that govern galaxies throughout the cosmos. The local group is the cluster of galaxies that includes the Via Lactea and comprises more than 50 galaxies spanning a diameter of approximately 10 million light-years. This cosmic neighborhood represents a diverse collection of galaxies ranging from spirals like the Via Lactea and the galaxy of Andromeda to dwarf galaxies like the small Melanica Cloud, Black Cloud, and the Great Black Cloud, which are some of the closest companions of the Via Lactea. The gravitational center of the local group is located somewhere between the Via Lactea and the galaxy of Andromeda, the two largest members of the group. These main galaxies, along with the galaxy of the Triangle, M33, which is the third largest, dominate the gravitational landscape of the local group, and their interactions play an important role in the cosmic dance of the smaller galaxies. One of the fascinating aspects of the local group is its demonstration of galactic interactions, including tidal forces and fusions. For example, the Via Lactea is currently interacting with the Sagittarius dwarf spheroidal galaxy, gradually separating it and assimilating its stars. Similarly, Andromeda has a history of absorbing its smaller neighbors. The study of the local group offers crucial information about the formation and evolution of galaxies, providing astronomers with a relatively close view of the processes that shape galaxies throughout the universe. Given its proximity, the local group serves as a natural laboratory for astronomers to understand the dynamics of galactic interaction, the distribution of dark matter, and the history of star formation in a variety of galactic environments. Through the study of the local group, astronomers can obtain a clearer picture of the vast and intricate network of galaxies of which our galaxy is only a unique, although very special, node. Galaxies, those expanding systems of stars, gas, dust, and dark matter that populate the universe, are formed and evolved through processes that have fascinated astronomers for decades. The current understanding is that galaxies begin as small density fluctuations in the early universe. After the Big Bang, The universe was an almost uniform hot soup of particles. Over time, slight density variations, mainly influenced by dark matter, began to gravitationally attract the surrounding matter. These overdensities grew and formed the cosmic web, a vast structure of filaments and voids. In the regions where these filaments intersected, dark matter and baryonic matter, the normal matter that makes up stars, planets, and us, joined, creating the gravitational wells necessary for the birth of galaxies. The gas inside these wells cooled and condensed, forming the first stars and seeding the galaxies with the crucial elements for the formation of planets and life as we know it. As the galaxies evolved, their growth was marked by episodes of star formation, supernova explosions, and the accretion of gas from the intergalactic medium. These processes, along with interactions and fusions with other galaxies, significantly influence their shapes and sizes. Galaxies can attract smaller satellite galaxies and merge them into their structure, a process that the Via Láctea is currently experiencing with several nearby dwarf galaxies. In addition, in the center of most, if not all, large galaxies, supermassive black holes exert their influence, sometimes extinguishing star formation in their host galaxies by heating and expelling gas. These black holes can also feed quasars and active galactic nuclei, making their host galaxies visible through vast cosmic distances over centuries. The rate of star formation and the dynamics of interaction between galaxies have sculpted the varied galactic landscape of the universe, from spiral galaxies like the Via Láctea to elliptical and irregular galaxies. This continuous cycle of birth, growth, interaction, and sometimes destruction, driven by gravitational forces, underlies the rich tapestry of the structure of the universe. Modern astronomy and astrophysics strive to unravel the complexities of galactic formation and evolution, bringing us closer to understanding the past, present, and future of the universe. The galaxy of Andromeda, our closest spiral neighbor, is a crucial object in the search for understanding the universe. By studying Andromeda, also known as M31, astronomers can obtain information about the structure, formation, and evolution of spiral galaxies, including our own Via Láctea. The proximity of Andromeda, about 25 million light-years away, allows detailed observations of its stars, dust, and gas, offering a comparative perspective not possible with more distant galaxies. One of the most valuable lessons from Andromeda concerns the life cycle of galaxies. The observations of Andromeda have revealed a complex history of interactions and fusions with smaller galaxies, shedding light on how galaxies grow and evolve over billions of years. These interactions have left traces in the form of stellar currents and disturbed structures in the halo of Andromeda, which provides direct evidence of the dynamic and, at times, violent nature of galactic evolution. In addition, Andromeda has a double nucleus and a huge central black hole, which offers a unique opportunity to study the dynamics of stars near a supermassive black hole and the processes that feed such black holes. The comparison of Andromeda's central role with the one found in the center of the Via Láctea helps astronomers understand the role these giants play in the life cycle of galaxies. In addition, the disk of Andromeda is sprinkled with regions of intense star formation along with older stellar populations that present a complete spectrum of stellar evolution processes. When studying these different stellar populations, scientists can reconstruct the history of star formation in the galaxy and draw parallels with star formation in the Milky Way. Finally, the eventual collision and merger between Andromeda and the Milky Way, which is predicted to occur within about 4 billion years, offers a destiny-filled glimpse into the future of our own galaxy. The study of Andromeda not only deepens our understanding of the cosmos, but also places the history and destiny of the Milky Way within the broader narrative of the continuous development of the universe. A dwarf galaxy is a small galaxy composed of between a few million and several billion stars, a fraction of the size of larger galaxies, such as the Milky Way, which contains hundreds of billions of stars. Despite its modest size, dwarf galaxies are of great interest to astronomers due to their abundance in the universe and their role in galactic evolution and cosmology. Dwarf galaxies can be found orbiting larger galaxies due to gravitational attraction, residing in galactic halos, or wandering through intergalactic space. These small galaxies present a great variety of shapes and compositions, including elliptical dwarf galaxies, which have a spheroidal shape, and irregular dwarf galaxies, which lack a clear structure and often have active regions of star formation. One of the key characteristics of dwarf galaxies is their high content of dark matter in relation to visible matter. This aspect makes them crucial laboratories for the study of dark matter, since their dynamics cannot be explained without resorting to this mysterious component. In addition, dwarf galaxies are often considered the building blocks of larger galaxies, shedding light on the processes that shaped the universe in its beginnings. The study of dwarf galaxies also provides information about the processes of star formation in conditions different from those of more massive galaxies. Their relatively simple structures and the presence of old stars make them excellent objects for understanding the chemical evolution of the universe. The local group, our own cosmic neighborhood, contains several dozens of dwarf galaxies, including the Small and Large Magellanic Clouds, which are some of the closest and best studied examples. The observations and investigations on these tiny galaxies contribute valuable information for our understanding of the formation of galaxies and the composition of the matter of the universe, which highlights the importance even of the smallest members of the cosmic family. Galaxies interact and merge through the force of gravity, which acts through vast distances in space, attracting galaxies toward each other. These cosmic encounters can drastically alter the structures and star formation rates of the galaxies involved, ultimately leading to their fusion into a single larger galaxy. The interaction process can last from hundreds of millions to more than 1 billion years, depending on the sizes and relative speeds of the galaxies. As galaxies begin to interact, their mutual gravitational attraction can distort their shapes, creating tides that drag long streams of stars and gas. These gravitational forces can trigger intense bursts of star formation as the clouds of gas collide and compress, creating new stars at a rapid rate. In addition to the stars that are born, existing stars can be launched into new orbits, creating tidal tails and bridges between the galaxies during the fusion. Supermassive black holes that reside in the center of most galaxies can get closer to each other and end up spiraling toward each other and merging. This process can release large amounts of energy and, in some cases, power active galactic nuclei or quasars. As the fusion progresses, the individual characteristics of the galaxy, such as spiral arms or bars, can blur and end up being lost, leading to the formation of a galaxy that may have a completely different structure. For example, many astronomers believe that the collision and fusion of galaxies can lead to the formation of elliptical galaxies. The interactions and fusions of galaxies play an important role in the cosmic cycle of matter and the evolution of galaxies. Throughout the universe, they are fundamental processes that drive the growth of galaxies, influence their star formation history, and reshape the structure of the universe on a large scale. Through the study of interacting and merging galaxies, astronomers can obtain information about the past and the future of the cosmos, including the destiny of our own Milky Way, which is heading toward an eventual fusion with the Andromeda Galaxy. Starburst galaxies are a captivating class of galaxies that experience exceptionally high rates of star formation that far exceed the star formation rates observed in typical galaxies like our own Milky Way. In these galaxies, the rate of star formation can be tens or even hundreds of times greater, leading to the rapid birth of millions or even billions of new stars in a relatively short astronomical period of time, often only a few million years. The catalysts for starburst activity can vary in many cases and are triggered by interactions or mergers with galaxies, such as the gas inside the galaxies, creating dense clouds where stars can form more easily. Gravitational interactions can also channel gas toward the nucleus of the galaxy, where it can trigger a frenetic period of star formation. However, starbursts can also occur in isolated galaxies, driven by internal processes that accumulate and compress the gas to the critical point necessary for star formation to ignite. Starburst galaxies are not only defined by their high star formation rates, but also by their luminosity. The newly formed massive stars are hot and bright and emit large amounts of ultraviolet light that can be shielded by the surrounding dust and re-emitted at infrared wavelengths, making starburst galaxies incredibly luminous, especially in the infrared part of the spectrum, although they may not be as visible at optical wavelengths due to the dust that obscures them. Starbursts are often ephemeral phenomena on cosmic time scales, lasting only a few tens of millions of years, as intense star formation can rapidly deplete available gas reserves or expel them from the galaxy, preventing the formation of new stars. The aftermath of a starburst can leave a dramatically transformed galaxy with a new population of young stars, altered gas dynamics, and, sometimes, a changed morphology. The study of starburst galaxies provides crucial information about the processes of star formation, the evolution of galaxies, and the dynamics of galactic interactions. These bright and fleeting phases in the life of a galaxy offer a vision of the vibrant and ever-changing nature of the universe. The Magellanic Clouds, composed of the Large Magellanic Cloud, LMC, and the Small Magellanic Cloud, SMC, are two of the most prominent satellite galaxies of the Milky Way, visible from the southern hemisphere. These irregular dwarf galaxies are of considerable importance in the study of astrophysics for several reasons. First, the Magellanic Clouds offer a nearby laboratory to study the processes of star formation and galactic evolution in an environment different from that of the Milky Way. Their relative proximity allows astronomers to observe individual stars, star clusters, ST, and nebulae with great detail. These observations have contributed to a deeper understanding of the life cycles of stars, the interstellar medium, and the dynamics of small galaxies. Secondly, the interactions between the Magellanic Clouds and the Milky Way provide crucial information about the behavior of galaxies over cosmic time. It is believed that the gravitational attraction between these galaxies has led to the formation of the Magellanic Stream, a long ribbon of gas that extends over hundreds of thousands of light years and that is dragged behind the clouds as they orbit the Milky Way. Studies of these interactions help astronomers understand the role of tidal forces in galaxy mergers and the accretion of satellite galaxies, a common phenomenon in the evolution of galaxies throughout the universe. In addition, the Magellanic Clouds have been fundamental in refining the cosmic distance scale. The observations of variable stars in the LMC, in particular, have been fundamental to calibrating the relationship between the Cepheid variability period and the luminosity. This relationship is a key step on the cosmic distance ladder that allows astronomers to measure distances to galaxies beyond the local group and, therefore, estimate the size and age of the universe. Nor can the historical importance of the Magellanic Clouds be underestimated. Known by the indigenous peoples of the southern hemisphere for millennia and reported for the first time to Europeans by explorers in the 16th century. Their study has played a central role in the development of modern astronomy, from the first observations in the southern hemisphere to contemporary research with state-of-the-art telescopes. The Magellanic Clouds are not only striking features of the night sky, but are also fundamental to our understanding of the cosmos. Their study has shed light on fundamental astrophysical processes and continues to influence our knowledge of the vast and dynamic nature of the universe. Galactic filaments are like a vast scaffolding of the universe, structures that extend through space for millions of light years and are composed of galaxies, gas, and dark matter. Let's imagine these filaments as immense cosmic threads that intertwine through the cosmos, joining galaxies in a gigantic celestial network. The existence of such structures dates back to the beginnings of the universe, shaped by the gravitational attraction of dark matter over billions of years. These filaments have grown, attracting galaxies towards their immense networks and guiding cosmic evolution. Scientific research, driven by advanced telescopes and sophisticated computer simulations, reveals that these filaments are not only static bridges in space, but are dynamic and pulsate with the flow of cosmic material. They play a crucial role in the life history of galaxies, influencing how they interact and evolve over cosmic time. It is through the study of galactic filaments that we begin to understand the large-scale structure of the universe and our place within this immense cosmic network. Superclusters are formed through the gravitational attraction of smaller groups and clusters of galaxies over billions of years, gradually merging into these vast cosmic structures that extend over hundreds of millions of light years. At the heart of their formation lies the mysterious dark matter, an invisible substance that constitutes approximately 85% of the mass of the universe. Dark matter creates the gravitational scaffolding on which ordinary matter accumulates, attracting galaxies towards each other in chains and knots that weave the cosmic network where superclusters arise. These superclusters are not just random conglomerations of galaxies, but are the largest coherent structures in the cosmos, shaped by the expansion of the universe and the gravitational dance of dark matter and galaxies as they travel along the intricate paths traced by the dark matter framework and meet others, leading to interactions and mergers that fuel the growth of superclusters. This ongoing cosmic evolution, a process that has been developing throughout the 138 billion years of cosmic history, offers a captivating vision of the forces that have sculpted the great architecture of the universe. The Virgo supercluster, an immense collection of groups and clusters of galaxies, is home to our own Via Láctea, our galaxy, nestled in this vast cosmic ensemble. Our galaxy is just one of the thousands, if not millions, that make up the intricate network of the structure. The supercluster extends about 110 million light years, making it a considerable entity, but not the largest in the cosmos, centered around the Virgo cluster, which contains more than 1,000 galaxies. The gravitational heart of the supercluster attracts galaxies towards it, acting as a cosmic anchor within the local universe. This structure is part of an even larger ensemble known as the Laniakea supercluster, which further highlights the interconnected hierarchy of matter in the universe. Understanding the place that the Virgo supercluster occupies in the cosmos provides a crucial perspective on the location and movement of the Via Láctea through space, emphasizing our interconnection in the great cosmic network. Astronomers trace the large-scale structure of the universe using a combination of sophisticated telescopes, observatories, and complex computer simulations. They collect the light from distant galaxies and analyze it to determine their positions, movements, and distances from Earth. Techniques such as redshift measurements play a fundamental role, since, as galaxies move away from us, their light stretches into longer and redder wavelengths, providing clues about their speed and distance. This cosmic detective work is complemented by studies that scan vast areas of the sky, cataloging galaxies and mapping their distribution across billions of light years. Advanced computer simulations based on theoretical physics and cosmological principles predict how matter should cluster and stretch across the universe under the influence of gravity, dark matter, and dark energy. By comparing these predictions with real observations, astronomers can refine their models and improve our understanding of the vast network of galaxies, clusters, and superclusters in the universe. This laborious process has revealed the great structure of the universe, a complex and beautiful cosmic network of matter woven through the fabric of space-time. Dark energy plays a fundamental role in the expansion of the universe, acting as a mysterious force that accelerates the growth of the cosmos, discovered through observations of distant supernovas in the late 1990s. Dark energy challenges the traditional understanding of gravity by separating galaxies instead of attracting them. It constitutes about 70% of the total energy content of the universe, eclipsing the combined contributions of all matter, both visible and dark. Unlike dark matter, which clusters and helps form the structure of the cosmic network, the effect of dark energy is smooth and uniform throughout space. Its discovery has led to a significant change in cosmological models, which emphasize that the fate of the universe is intimately linked to the properties of this enigmatic force, as the universe expands under the influence of dark energy. Understanding its nature is crucial to unraveling the past, present, and future of the cosmos. Despite its ubiquitous effect, dark energy remains one of the deepest mysteries of astronomy, stimulating research and debates in the search for understanding the structure of the universe. The cosmic microwave background, CMB, is the residual radiation from the Big Bang that filled the universe approximately 380,000 years after its explosive start. Before that moment, the universe was a hot, dense plasma of electrons, protons, and photons. At this crucial moment, known as the era of recombination, the universe cooled enough for protons and electrons to combine into neutral hydrogen, allowing photons to travel freely without being constantly scattered by electrons. These photons, stretched by the expanding universe, have cooled for billions of years to reach microwave wavelengths, creating a faint but ubiquitous glow across the sky. The CMB provides a snapshot of the infant universe, offering astrophysicists fundamental clues about its composition, age, and the fundamental processes that have shaped its evolution. Accidentally discovered in 1964 by Arno Penzias and Robert Wilson, the uniformity and slight fluctuations of the CMB have been extensively studied, leading to revolutionary discoveries about the early moments of the universe and confirming key predictions of the Big Bang theory. The cosmic microwave background, CMB, is a treasure trove of information about the early universe, offering a direct view of its state when it was only 380,000 years old. The slight fluctuations or variations in the temperature of the CMB provide evidence of the initial density variations that would eventually lead to the formation of galaxies, stars, and other cosmic structures. These tiny temperature variations, typically on the order of 1 part per 100,000, serve as seeds from which all cosmic structures have grown, shaped by the forces of gravity and dark matter over billions of years. In addition, the uniformity of the CMB has confirmed the predictions of the Big Bang theory, demonstrating that the universe was surprisingly homogeneous in its infancy. The analysis of the CMB also allows cosmologists to measure the basic parameters of the universe with remarkable precision, such as its age, the speed of its expansion, and the composition of matter and energy it contains. For example, the CMB has been fundamental to determining that dark matter and dark energy together constitute the greater part of the total energetic content of the universe, while ordinary matter constitutes only a small fraction. In addition, the polarization of the CMB, or the way light waves vibrate, provides information about the conditions of the early universe, including tests of the inflationary theory, which postulates a rapid exponential expansion of the universe moments after the Big Bang. So the CMB serves as a cornerstone of modern cosmology, a cosmic relic that continues to reveal the mysteries of the infancy of the cosmos and its subsequent evolution. The fluctuations in the cosmic microwave background, CMB, are immensely informative for cosmology since they offer a detailed understanding of the structure and composition of the universe. These fluctuations, or anisotropies, represent small temperature variations throughout the CMB and are believed to arise from quantum fluctuations in the early universe that were magnified during the period of inflation. They serve as initial conditions for the large-scale structure of the universe, acting as seed from which galaxies and galaxy clusters grew, driven by the gravitational attraction of dark matter. The detailed study of these fluctuations has allowed cosmologists to refine the standard model of cosmology. For example, the scale of the fluctuations provides information about the geometry of the universe, revealing it to be flat with a high degree of precision. This flatness implies that the total density of the universe is very close to the critical density necessary to halt its expansion and highlights the important role of dark energy in the accelerated expansion of the universe. In addition, the relative amplitudes of temperature fluctuations at different angular scales provide crucial information about the composition of the universe, such as the proportion of ordinary matter with respect to dark matter and dark energy. They also offer information about the physics of the early universe, including the conditions that led to the rapid expansion known as inflation. The polarization patterns within the CMB further enrich our understanding, revealing details about the age of the universe, the history of ionization, and even hints of gravitational waves from the inflationary era. In essence, the fluctuations in the CMB serve as a cosmic blueprint that catalogs the fundamental characteristics of the universe and guides the development of theoretical models. Through the study of these ancient light patterns, cosmologists can reconstruct the evolutionary history of the universe, which makes the CMB an indispensable tool in the search for the understanding of the cosmos. The formation of the universe is a profound mystery that has intrigued humanity for centuries, leading to the development of several theories that aim to explain this monumental event. Among the most prominent is the Big Bang theory, which postulates that the universe began as an infinitely dense and hot singularity about 138 billion years ago. According to this theory, the universe has been expanding and cooling since then, a notion supported by substantial observational evidence, such as the redshift of distant galaxies and the cosmic microwave background radiation. Another intriguing theory is cosmic inflation, an extension of the Big Bang theory that suggests that the universe underwent a brief but exponential expansion in fractions of a second after its birth. This rapid expansion would explain why the observable universe appears flat, homogeneous, and isotropic on a large scale. Inflation predicts the existence of quantum fluctuations that gave rise to the formation of the cosmic structures that we observe today. There are also alternative theories that explore the origins of the universe, such as the cyclic model, which proposes that the universe undergoes endless cycles of expansion and contraction, discarding the idea of a singular beginning. Meanwhile, string theory and M-theory introduce the concept of the multiverse, suggesting that our universe could be one of many within a vast and possibly infinite cosmic landscape. Although the Big Bang theory remains the most widely accepted explanation, cosmologists continue to investigate and refine these theories using advanced technology and mathematics to probe the limits of the known universe. As our understanding deepens and new evidence comes to light, our theories about the formation of the universe evolve, reflecting the dynamic nature of scientific research. A quasar, abbreviation of quasi-stellar object, is an extraordinarily bright and distant galactic radio source, powered by a supermassive black hole in its center. Despite its compact size comparable to that of our solar system, quasars are among the most luminous objects in the universe, emitting light and energy throughout the electromagnetic spectrum, from radio waves to gamma rays. The immense energy emitted by quasars, which often eclipses entire galaxies, originates in the accretion disk of material that spirals into the black hole. As the matter in the disk falls into the black hole, it heats up to incredible temperatures, releasing enormous amounts of energy in the process. Quasars were discovered in the 1960s as mysterious radio sources. Subsequent observations revealed their true nature as centers of distant galaxies that provide a window into the conditions of the early universe. The light from quasars takes billions of years to reach us, which means that we observe them as they existed in the past, offering us valuable information about the formation and evolution of galaxies and supermassive black holes. In addition, the distribution and properties of quasars throughout the universe play a crucial role in testing cosmological models and theories about the structure and expansion of the cosmos. Despite their distant nature, quasars remain one of the most fascinating topics in astrophysics. Uniting the history of cosmic evolution from the early universe to the present day, an active galactic nucleus, AGN, and a quasar represent energetic and luminous phenomena that occur in the centers of galaxies, driven by the accretion of supermassive black holes. The main difference between them resides in its intensity and visibility from Earth. Quasars are essentially a type of highly luminous AGN and are often considered the most energetic and distant member of the AGN family. Quasars can eclipse their host galaxies by emitting light and energy across a broad spectrum, making them visible across vast cosmic distances. The term active galactic nucleus is a broader classification that includes various types of active nuclei, such as safer galaxies, radio galaxies, and blazars, in addition to quasars. AGNs vary significantly in their luminosity, size, and the wavelengths in which they emit most intensely. Its activity is measured by the rate at which material accumulates in the central supermassive black hole, with quasars representing the extreme of this spectrum, while quasars are often considered a subclass within the broader category of AGN. All these phenomena share the common characteristic of having an engine driven by a supermassive black hole in its nucleus. However, observational characteristics, such as brightness, distance to Earth, and the angle from which they are observed, can lead to their classification as different types of AGNs, highlighting quasars for their exceptional luminosity and energy production. The extraordinary luminosity of objects such as quasars and active galactic nuclei, AGN, is driven by the gravitational energy released when matter accumulates or falls into a supermassive black hole in the center of the galaxy. When gas, dust, and stars are attracted to the black hole, they form a spiral structure known as an accretion disk. The intense gravitational forces at play heat the material in the accretion disk to millions of degrees, causing it to emit an enormous amount of light and other forms of radiation throughout the electromagnetic spectrum. This process is very efficient at converting gravitational potential energy into electromagnetic radiation, much more so than the nuclear fusion that powers the stars. The closer the material gets to the event horizon or point of no return, the faster it moves and the hotter it gets, leading to the emission of even more energy in the most luminous AGNs and quasars, whose brightness can exceed that of all the stars in the host galaxy together, making them visible across vast cosmic distances beyond the electromagnetic radiation. The accretion process can also drive powerful jets of charged particles at speeds close to that of light, which extend far beyond the limits of the galaxy. These jets contribute even more to the luminosity of the AGNs, especially in the radio and gamma-ray wavelengths. The interaction of the intense gravitational forces, the physics of the accretion disks, and the extreme conditions near supermassive black holes are what make quasars and AGNs among the brightest objects in the universe. Quasars and active galactic nuclei, AGN, are detected by various observation techniques spanning the entire electromagnetic spectrum, taking advantage of their immense brightness and energetic emissions. Initially, many quasars were discovered as radio sources in the early days of radio astronomy. These objects stood out for their quasi-stellar appearance, but emitted unusually strong radio waves. As observation techniques improved, advanced astronomers began to identify quasars and AGN through their unique spectral signatures, particularly the broad emission lines that indicate the high speed of gas in the vicinity of the supermassive black hole. Modern detections often involve multi-wavelength observations. Infrared studies can unearth AGN obscured by dust that visible light cannot penetrate. X-ray observatories detect high-energy emissions from the hot accretion disks around black holes, a hallmark of AGN activity. Similarly, space-based gamma-ray telescopes reveal the most energetic phenomena associated with quasars and AGN, such as relativistic jets. Large-sky surveys using sophisticated telescopes equipped with sensitive detectors and covering multiple wavelengths have significantly increased the number of known quasars and AGN. These studies catalog vast areas of the sky and identify candidates based on their luminosity, color, and spectral properties. Follow-up observations with more powerful telescopes provide the detailed measurements needed to confirm their nature. The combination of wide-field surveys and specific observations throughout the electromagnetic spectrum allows astronomers to detect and study these luminous beacons, revealing their properties and the extreme physics that powers them. Quasars provide a unique window into the early universe, serving as cosmic beacons that illuminate the conditions and processes that occurred when the cosmos was in its infancy. Since quasars are among the most distant and luminous objects known, their light has traveled billions of years to reach us, which means that we observe them as they were when the universe was significantly younger. By studying quasars, astronomers can gain information about several key aspects of the early universe. First, the very existence of quasars in the distant past, powered by supermassive black holes with masses of millions to billions of times that of the Sun, challenges our understanding of the formation and growth of black holes. These observations imply that supermassive black holes formed and grew to immense sizes much faster than current theoretical models can fully explain, suggesting rapid accretion or perhaps novel mechanisms at play in the universe. Second, by analyzing the light from quasars, astronomers can study the intergalactic medium, IGM, that lies between galaxies. The light from quasars passing through the IGM is absorbed by elements such as hydrogen, leaving distinctive spectral lines that provide clues about the state of the universe at different times. This includes insights into the era of reionization, a transformative period in which the first stars and galaxies ionized the neutral hydrogen that fill the universe, ending the cosmic dark age. In addition, the distribution and density of quasars in the sky help cosmologists understand the large-scale structure of the universe and the role of dark matter in the formation of galaxies. Since quasars are associated with galaxies, so their spatial distribution can be used to trace the underlying dark matter network that determines the structure of the cosmos. Finally, the study of quasars contributes to refining cosmological models, including measuring the expansion rate of the universe and understanding the influence of dark energy. Their extreme brightness allows for precise measurements at great distances, serving as beacons that shed light on the expansion of the universe. Quasars are invaluable probes of the early universe, offering information about the formation and evolution of the first massive objects, the state of the intergalactic medium, and a large-scale structure of the cosmos, while helping to refine our understanding of fundamental cosmological principles. Dark matter is a mysterious and invisible form of matter that exerts gravitational attraction, but does not emit, absorb, or reflect light, making it completely undetectable by conventional electromagnetic means. Despite its elusive nature, dark matter is believed to make up about 85% of the total matter in the universe, a significantly larger amount than the ordinary matter that makes up stars, planets, and living things. The existence of dark matter was first deduced from observations of galaxies and galaxy clusters. Astronomers observed that the gravitational effects within these structures could not be explained by visible matter alone. For example, galaxies rotate at speeds such that they would disintegrate unless there was a significant amount of invisible mass providing the gravitational force to hold them together. Similarly, galaxy clusters exhibit gravitational binding forces that indicate the presence of much more mass than can be accounted for by the visible galaxies within them. In addition to its gravitational effects on a cosmic scale, dark matter also plays a crucial role in the formation and evolution of cosmic structures. Theories of cosmic structure formation suggest that dark matter clumped together in the early universe to form a cosmic web of dark matter halos. These halos provide the gravitational scaffolding on which ordinary matter congregates, eventually leading to the formation of stars and galaxies. Despite exhaustive searches, the precise nature of dark matter remains unknown and is one of the most pressing mysteries in current astrophysics and cosmology. Several hypothetical particles have been proposed as dark matter candidates, including weakly interacting massive particles, WIMPs, and axions, but none have been definitively detected. Understanding dark matter is crucial for a complete picture of the composition of the universe, its formation, and its ultimate destiny. The discovery of dark matter, a mysterious and invisible substance that makes up approximately 27% of the universe, is a story that intertwines astrophysics and serendipity, dating back to the early 20th century, when Swiss astronomer Fritz Zwicky observed the Coma cluster, a massive grouping of galaxies. Zwicky used the virial theorem, a principle that relates the total kinetic and potential energies of a system, to estimate the total mass of the cluster. His calculations revealed something surprising. Visible matter, such as stars and galaxies, accounted for only a fraction of the total mass needed to exert the gravitational forces that held the cluster together. This discrepancy suggested the presence of an invisible matter that Zwicky aptly named dark matter. However, this revolutionary idea was ignored for decades, considered more of an anomaly than a discovery. It was not until the 1970s, when Vera Rubin and Kent Ford mapped the rotation curves of spiral galaxies, providing more evidence for the existence of invisible mass, that the astronomical community began to seriously consider the existence of dark matter. Their observations showed that stars on the outskirts of galaxies moved as fast as those near the center, defying Newtonian mechanics unless there was significantly more mass in the galaxies than was visible. This was the turning point that transformed dark matter from a speculative theory to a major scientific pursuit that restructures our understanding of the composition of the universe. In the quest to detect dark matter, scientists have deployed a variety of innovative experiments around the world, each designed to glimpse this elusive substance. One of the main methods involves the use of incredibly sensitive detectors placed deep underground to protect them from cosmic rays and other forms of interference. The Large Underground Xenon Experiment, LUX, is located nearly a mile below the Earth's surface at the Sanford Underground Research Facility in South Dakota, USA. EU is one of those. Its goal is to detect dark matter particles when they collide with xenon atoms within the detector. Another revolutionary experiment is the Alpha Magnetic Spectrometer AM02, a particle detector of the latest generation physics that operates on the International Space Station. It looks for indirect evidence of the existence of dark matter through the analysis of cosmic rays, searching for unusual patterns or excesses of particles that could be byproducts of dark matter collisions or decay. Meanwhile, on a contrasting but complementary front, the Axion Dark Matter Experiment, ADMX, explores the possibility that dark matter may be composed of hypothetical particles called axions, which are considerably lighter than those sought by other experiments. Using a strong magnetic field and a sensitive antenna, ADMX listens for the faint signal of axions converting into microwave photons. These diverse approaches not only underscore the complexity and challenge of detecting dark matter, but also the vibrant creativity and persistence of the scientific community. Each experiment, with its unique methodology and technology, expands the frontier of knowledge and brings us closer to unveiling the nature of dark matter, one of the greatest mysteries of the cosmos. Dark energy is an enigmatic force that has captivated cosmologists and astronomers alike, offering a compelling explanation for the accelerated expansion of the universe, which represents approximately 68% of the total energy of the universe. Dark energy remains largely invisible and undetectable by direct observation. Its existence was proposed after the surprising discovery in the late 1990s that the rate at which the universe expands was not slowing down as would be expected due to the gravitational attraction of matter, but accelerating. This surprising revelation was discerned through observations of distant supernovas that serve as cosmic yardsticks, revealing the expansion rate of the universe over time. Unlike dark matter, which exerts gravitational attraction, dark energy appears to have a repulsive effect that separates galaxies with a force exceeding the gravitational attraction that tries to bring them together. The nature of dark energy is one of the greatest enigmas of modern cosmology, with theories ranging from a cosmological constant, a concept introduced by Albert Einstein as an anti-gravity force to balance gravity and achieve a static universe, to more exotic proposals involving new fields and forces beyond our current understanding of physics. As such, dark energy not only challenges our understanding of the composition of the cosmos, but also our fundamental theories of physics, hinting at new laws and principles that govern the vast expanse of the universe. Scientists continue to investigate the mystery of dark energy, striving to understand its properties and its profound implications for the destiny of the universe. Dark energy plays a fundamental role in shaping the large-scale structure and destiny of the universe through its influence on the cosmic expansion rate. This mysterious form of energy that permeates all space exerts a repulsive force that accelerates the expansion of the universe. This acceleration was a revolutionary discovery in the late 20th century that completely changed our understanding of the evolution of the universe. Before this, scientists thought that the expansion of the universe born from the Big Bang would gradually slow down under the influence of the gravity of all the mass of the universe. Instead, observations of distant supernovas revealed that galaxies are moving away from each other at an ever-increasing rate. The effect of dark energy on cosmic expansion can be compared to an invisible hand stretching space itself, causing galaxies to move away from each other faster as time passes. This has profound implications for the future of the universe. If dark energy continues to dominate, the universe could continue to expand indefinitely, becoming colder and emptier as galaxies move away from each other. This scenario leads to a rather lonely and desolate long-term perspective known as the Big Freeze or heat death, in which the universe reaches a state of maximum entropy. Understanding dark energy and its effects on cosmic expansion is not only about charting the current state of the universe, but also about unraveling the mysteries of its ultimate destiny. Gravitational waves are ripples in the fabric of space-time, caused by some of the most violent and energetic processes in the universe. Imagine throwing a stone into a pond and see how the waves spread from where it has fallen. Gravitational waves are similar. They spread from the source, but instead of traveling through water, they move through the very fabric of the universe. They were first predicted by Albert Einstein in 1916 as a consequence of his general theory of relativity. According to Einstein, when massive objects such as black holes or neutron stars collide, they can send shock waves through the cosmos, bending and stretching space-time as they propagate at the speed of light. Detecting these incredibly subtle waves is a monumental challenge that scientists have managed to overcome by building incredibly sensitive detectors. The most famous of these is the Laser Interferometer Gravitational Wave Observatory, LIGO, which operates two detectors, one in Hanford, Washington, and the other in Livingston, Louisiana. These detectors work by using laser beams sent through long perpendicular tunnels to measure minute changes in distance caused by the passage of a gravitational wave. The precision of these measurements is mind-boggling. LIGO can detect changes in length smaller than 1/1000 the diameter of a proton. This extraordinary sensitivity allowed the first direct detection of gravitational waves in 2015, a century after Einstein first predicted them, confirming a key prediction of general relativity and opening a new window into the cosmos. This detection not only represented a monumental achievement in physics, but also heralded the beginning of gravitational wave astronomy, which allows us to observe and understand cosmic events billions of light years away in a completely new way. Since the historic first detection of gravitational waves in 2015, these cosmic waves have become a revolutionary tool that has ushered in a new era of astronomy, leading to several revolutionary discoveries. Among the most spectacular is the observation in 2017 of two neutron stars colliding in a galaxy 130 million light-years from Earth. This event, known as a kilonova, not only emitted gravitational waves, but was also observable through traditional electromagnetic means, including visible light, radio, and gamma rays. This multi-messenger observation was a scientific milestone that provided direct evidence that such collisions produce heavy elements such as gold and platinum, offering critical information about the chemical evolution of the universe. Another notable discovery came from the detection of gravitational waves from the collision of two black holes, each weighing around 30 times the mass of the Sun. This event provided the first solid evidence of the existence of intermediate mass black holes, filling a long-standing gap in the understanding of the formation and evolution of black holes. In addition, the detection of gravitational waves has allowed scientists to test aspects of Einstein's theory of general relativity under extreme conditions, confirming its predictions with remarkable precision and shedding light on the behavior of space and time near these enigmatic objects. These discoveries are just the tip of the iceberg of what gravitational waves can reveal about the universe. Each new detection is a potential treasure trove of information that allows researchers to probe the most extreme environments of the cosmos, from the densest matter to the earliest moments after the Big Bang. As detection techniques are refined, we can expect gravitational wave astronomy to continue to transform our understanding of the universe, revealing secrets that have remained hidden for billions of years. Neutrino astronomy represents an exciting frontier in our quest to unravel the mysteries of the universe, promising to significantly enhance our understanding of the cosmos. Neutrinos are nearly massless and uncharged particles that are produced in abundance in nuclear reactions such as those that power the Sun, supernova explosions, and the violent cores of distant galaxies. Due to their lack of charge and incredibly small mass, neutrinos interact very weakly with matter, allowing them to traverse the vast expanses of space unhindered, carrying pristine information from their point of origin. This unique characteristic makes neutrinos exceptional cosmic messengers that offer a view of phenomena that remain hidden from traditional telescopes. The advent of neutrino astronomy could fundamentally transform our understanding of the most energetic and enigmatic events in the universe. For example, the detection of neutrinos from the early universe could provide a new window into the conditions moments after the Big Bang, potentially shedding light on dark matter, the formation of galaxies, and the fundamental forces that govern the cosmos. Similarly, observing neutrinos from supernova explosions would allow astronomers to closely observe the mechanisms that drive these colossal events, including nuclear reactions and the formation of neutron stars or black holes. In addition, neutrino detectors could also play a key role in multi-messenger astronomy, working with gravitational wave observatories and electromagnetic telescopes to provide a more holistic view of cosmic events. This could lead to advances in understanding high-energy cosmic rays, the behavior of matter under extreme conditions, and even the fundamental properties of neutrinos, which remain one of the greatest unknowns in particle physics. In essence, neutrino astronomy promises to open new perspectives on the universe, challenging our current theories and unveiling aspects of the cosmos that have remained hidden or little known. The possible discoveries are central to the most pressing questions of cosmology, astrophysics, and particle physics, and could redefine our place in the universe. The James Webb Space Telescope, JWST, considered the most powerful space telescope ever built, fulfills multiple fundamental functions in the advancement of knowledge and cosmic exploration. As a scientific successor to the Hubble Space Telescope, the JWST is designed to observe deeper into the universe and with greater clarity, taking advantage of its sophisticated set of infrared instruments. This capability allows it to look back in time more than 135 billion years to observe the first galaxies that formed after the Big Bang, providing crucial information about the structure and evolution of the early universe. These observations are fundamental to understanding how galaxies, stars, and planetary systems form and evolve throughout cosmic time. Beyond its quest to unravel the mysteries of the early universe, the JWST plays a key role in studying exoplanets and their atmospheres. Its instruments are finely tuned to detect and analyze light from stars as it passes through exoplanet atmospheres, revealing their chemical composition, temperature, and weather patterns. This information is crucial for identifying potentially habitable planets and understanding the diversity of planetary systems. In addition, the JWST observations will contribute significantly to studying objects within our own solar system, from Mars and beyond, by examining planets, moons, and other bodies in unprecedented detail. The JWST will enhance our understanding of the solar system's origins and the processes that have shaped it over billions of years. The functions of the James Webb Space Telescope range from probing the early universe to studying the atmospheres of distant exoplanets and exploring our solar system. Its capabilities promise to solve some of astronomy's deepest mysteries and raise new questions about the nature of the cosmos, placing it at the forefront of astronomical research for years to come. The Event Horizon Telescope, EHT, is a cutting-edge astronomical project that uses a global network of radio telescopes to create a virtual telescope the size of the Earth by combining data from these telescopes located around the world. The EHT achieves an angular resolution capable of observing objects on a scale previously thought impossible. This technique, known as Very Long Baseline Interferometry, VLBI, allows astronomers to study the universe's extreme environments in extraordinary detail. One of the most significant achievements of the EHD was the capture of the first image of an event horizon of a black hole in 2019. This revolutionary observation was made of the supermassive black hole at the center of the galaxy M87, located about 55 million light-years from Earth. The image showed a bright ring of gas and dust surrounding a dark central region, the black hole shadow, providing visual proof of an object predicted by Einstein's theory of general relativity, but never seen before. The ability to directly observe a black hole's event horizon opens new avenues to test fundamental physics under extreme conditions, including the laws of general relativity, quantum mechanics, and our understanding of the most mysterious and powerful objects in the universe. In addition, current and future EHD observations aim to delve deeper into the dynamic environment around black holes, investigate the processes that drive jets of particles traveling at nearly light speed, and continue to explore the physics that governs these cosmic titans. The Event Horizon Telescope has not only provided a visual confirmation of black holes, but has also ushered in a new era of high-resolution observational astrophysics, expanding our ability to study the most enigmatic phenomena in the universe. The question of whether other universes exist beyond our own is one of the most intriguing and speculative topics in modern cosmology, touching on science, philosophy, and even science fiction. This idea, often referred to as the multiverse theory, suggests that our universe may be just one of an immense, possibly infinite, number of universes that make up a larger multiverse. Each of these universes could have different physical laws, constants, and structures. Several theoretical frameworks suggest the possibility of other universes. For example, the theory of cosmic inflation, a rapid expansion of the universe after the Big Bang, could allow the formation of miniature universes within an expanding multiversal foam. Another approach comes from string theory, a branch of theoretical physics that postulates the existence of multiple hidden dimensions in addition to our familiar four-dimensional spacetime. In some versions of string theory, what we perceive as our universe could be one of many three-dimensional branes floating in a higher dimensional space, which could lead to scenarios in which multiple universes exist. Despite these intriguing theoretical possibilities, it is important to note that, for now, there is no direct empirical evidence to support the existence of other universes outside our own observable universe. The nature of the theory itself makes it difficult to verify, since, by definition, we would not be able to access other universes using any known means of observation or experiment. The idea of the multiverse remains a highly speculative but fascinating frontier of cosmology that challenges our understanding of reality and invites us to reflect on the nature of existence and the scope of physical laws. The search for evidence or theoretical confirmation of other universes continues to drive some of the most profound and existential research in current science. The multiverse theory is a captivating concept in cosmology that suggests the existence of multiple, perhaps even an infinite number of universes beyond our own observable universe. Each of these universes, according to the theory, could have different physical laws, constants, and characteristics, which could lead to a great diversity of physical realities. The notion of the multiverse broadens the perspective on the cosmos by proposing that what we consider the totality of existence, the universe, is only one of many. Thus, several scientific theories give rise to the concept of the multiverse. A prominent example is the theory of inflation, which postulates that the early universe underwent rapid expansion that could have created bubbles or parallel universes within a larger space. Another theoretical foundation of the multiverse comes from string theory, which suggests the existence of additional spatial dimensions and that our universe could be a membrane or brane within a higher dimensional space, which could lead to a landscape of multiple brane worlds. Critics of the multiverse theory point to its speculative nature and the current lack of empirical evidence or clear mechanisms to verify its predictions. However, its defenders argue that the multiverse could offer explanations for fine-tuning problems in physics, such as why the constants of nature appear to be precisely calibrated for the emergence of life. Although still in the realm of theoretical physics and not universally accepted, the multiverse theory represents a bold attempt to understand the ultimate nature of reality, expanding the limits of human thought about the cosmos. The concept of wormholes has its roots in the equations of the general theory of relativity of Einstein, which suggests that these hypothetical tunnels through space-time could exist in theory. Wormholes are conceived as bridges that connect two different points in space-time, which would allow one to travel instantly through vast cosmic distances or even between universes. This idea not only captivates the imagination, but also offers a tempting glimpse into a mechanism to travel faster than light, at least within the scope of mathematical models and theoretical physics. Theoretical physicists have proposed several types of wormholes, the most famous being the traversable wormhole, which would allow matter to pass from one end to the other. For a wormhole to be traversable and stable, theoretical constructions, such as exotic matter, are considered necessary. This matter would possess negative energy density and pressure to prevent the wormhole from collapsing. However, the existence of such exotic matter and the feasibility of creating or maintaining wormholes with it remain purely speculative. There is no empirical evidence of wormholes, and their existence remains a subject of theoretical exploration and debate. The study of wormholes touches on some of the deepest questions in physics, challenging our understanding of the fundamental nature of the universe and the limitations of space and time. If wormholes existed and were traversable, the implications for space travel and communication at interstellar distances would be revolutionary. However, until we find evidence or develop technologies that can detect or create wormholes, they will remain a fascinating speculation at the intersection of physics, astronomy, and the quest to understand the deepest mysteries of the cosmos. Theories about the final destiny of the universe have captivated scientists and philosophers for centuries, raising big questions about the future of existence itself. Modern cosmology offers several scenarios about how the universe could end, depending on its rate of expansion and the nature of dark energy. One of the main theories is the Big Crunch, in which the expansion of the universe eventually stops and reverses, leading all matter to collapse back into a singular point, and could lay the foundation for another Big Bang. This result depends on the density of the universe and whether gravity can overcome the expansion driven by dark energy. In contrast to the Big Crunch is the scenario of the Big Freeze or heat death, which many cosmologists currently consider more likely due to observations that the expansion of the universe is accelerating. In this model, the universe would continue to expand indefinitely, becoming colder and emptier over trillions of years as the stars go out and the galaxies separate. Eventually, the universe would reach a state of maximum entropy in which there would be no thermodynamic energy left to drive processes that would increase order. Another intriguing possibility is the Big Rip, in which the expansion of the universe accelerates to such an extent, driven by the repulsive force of dark energy that tears apart galaxies, stars, planets, and eventually space-time itself. This scenario depends on the nature of dark energy and whether its strength increases over time. Finally, theories such as that of the cyclic universe propose that the universe experiences an infinite cycle of big bangs and big crunches, suggesting a timeless oscillation through stages of expansion and contraction. Each of these theories reflects our current understanding of physical laws and cosmic measurements, which encompass both the uncertainties and the wonder. As observations become more precise, and as our theoretical frameworks evolve, our vision of the final destiny of the universe could change, continuing the search for answers to one of humanity's deepest questions. Cosmic strings are theoretical defects in space-time predicted by some models of the early universe that incorporate ideas from particle physics. If they exist, cosmic strings are incredibly thin, almost one-dimensional objects with an immense density that extend across the universe. They are believed to have formed during phase transitions in the early universe, similar to cracks that can appear in ice when water is released, But on a cosmic scale, these objects could offer profound insights into the unification of fundamental forces and the conditions of the early universe, challenging and refining current physical models in various ways. First, the detection of cosmic strings could provide direct evidence of grand unified theories, which attempt to unify three of the four fundamental forces of nature: the electromagnetic force, the weak nuclear force, and the strong nuclear force, into a single theoretical framework. Cosmic strings would be relics of the symmetry-breaking events predicted by these theories, offering tangible proof of physics beyond the standard model. In addition, cosmic strings could challenge our understanding of gravitational phenomena, as they are predicted to produce significant gravitational effects, such as gravitational lensing, which deflects light in a way that could cause distant objects to appear in multiple locations in the sky in ways that are not explained by conventional models. Gravitational waves emitted by oscillating or colliding cosmic strings could provide a unique signature that, if detected by observatories such as LIGO or future space detectors, would challenge and enhance our understanding of both gravitational physics and cosmology. Finally, cosmic strings could influence the formation of structures in the universe, playing a role in the distribution of galaxies and clusters. The study of these effects could challenge our current cosmological models and require new approaches to accurately understand the evolution of the universe. In essence, cosmic strings represent a tempting possibility at the intersection of quantum field theory cosmology and astrophysics. Their discovery would not only challenge but also revolutionize our understanding of the fundamental principles governing the universe, providing key insights into the structure of space-time, the nature of fundamental forces, and the history of the cosmos itself. Astrophysics, a field at the forefront of exploring the depths of the universe, is plagued with unresolved problems that challenge our understanding. These enigmas range from the very small to the unimaginably large, and touch almost every aspect of our understanding of the cosmos. One of the most prominent unresolved problems is the nature of dark matter and dark energy. Despite constituting about 95% of the total mass and energy content of the universe, their properties remain unknown. Dark matter, which exerts gravitational influence but does not emit, absorb, or reflect light, baffles scientists as to its composition. Dark energy, even more mysterious, drives the accelerated expansion of the universe by opposing the force of gravity. Understanding these components is fundamental to understanding the structure of the universe. Evolution and destiny are another major challenge, such as the enigma of black hole singularities and the information paradox. The centers of black holes, where current physical theories fall apart and predict infinite densities, challenge our understanding of the fabric of space-time. The information paradox, related to whether information that falls into a black hole is lost forever, challenges the principles of quantum mechanics and general relativity. The problem of cosmic inflation, the theorized exponential expansion of the universe just after the Big Bang, also raises unanswered questions. While this theory explains the uniformity of the cosmic microwave background radiation and the large-scale structure of the cosmos, details of the inflationary process and what drove it remain speculative. The detection and understanding of the origin of ultra-high-energy cosmic rays that hit Earth, with energy levels far exceeding those that current man-made accelerators can reach, is another mystery. Identifying their origins and acceleration mechanisms could reveal new physics beyond the standard model. Finally, the enigma of the expansion rate of the universe, known as the Hubble tension, challenges cosmological observations of the early universe through the cosmic microwave background and the current expansion rate using supernovas as standard candles, as they yield different results, suggesting that new physics could be at play. All these unanswered questions drive contemporary astrophysics research agendas, spurring the development of new technologies, observations, and theories that continually reshape our understanding of the cosmos. Venturing into the next trillions of years, we embark on a journey into the abyss of cosmic predictions, where theories intertwine with the fabric of the universe. On this timescale, we anticipate the stars will dim, giving way to a phase often described as the degenerate era. By this time, most stars that shine in our night sky will have exhausted their nuclear fuel, becoming white dwarfs, neutron stars, or black holes. These remnants of stellar glory will dot the universe, emitting a faint glow as they cool over eons. The galaxies as we know them will have changed drastically due to gravitational redshift, which will cause them to recede from each other, isolating themselves in a vast, expanding cosmos. Meanwhile, black holes will become the ultimate cosmic cemeteries, slowly engulfing the remains of celestial matter and even each other. The most mind-boggling aspect is perhaps the slow but inevitable process known as Hawking radiation, which is predicted to cause these black holes to evaporate over timescales inconceivable to the human mind, which could lead to a universe characterized by cold, dark, and desolate silence. This vision of the future of a universe, although imbued with scientific theory, is a humble reminder of the ephemeral nature of existence in this vast cosmos. As the last stars of the universe approach their final chapter, the cosmic stage is set for a slow fade into darkness. These last bastions of light, mainly low-mass stars such as red dwarfs, which burn their fuel with impressive frugality, will eventually exhaust their nuclear fusion capacity. Their disappearance does not begin with an explosion, but with a whisper. As these stars exhaust their last hydrogen fuel, their core contracts while the outer layers expand and go on to become white dwarfs, dense remnants of stars the size of the Earth that are no longer capable of nuclear fusion. These stellar relics then embark on a slow, cooling journey that extends over billions of years. Their brightness gradually dims, fading as they emit their remaining heat into the surrounding space. Over time, they will cool to a point where they no longer emit significant heat or light, transforming into black dwarfs, theoretical celestial bodies that stand as cold and dark monuments of the stellar era. This scenario leads to a universe where the lights have gone out almost completely, giving way to a cosmic era dominated by these silent and nearly invisible remnants of stars. This process summarizes the serene but somber end of stellar evolution in the cosmos. In the twilight of the universe, as it expands and cools, the fate of black holes emerges as a moving epilogue to cosmic giants. The theoretical predictions of the cosmic giants depend on an extraordinary process known as Hawking radiation, a concept proposed by physicist Stephen Hawking in the mid-1970s. According to this theory, black holes are not the eternal prisons they were believed to be, but slowly evaporate, emitting radiation and particles over incomprehensibly long timescales. This radiation arises from the effects of quantum mechanics near the event horizon, the boundary beyond which nothing can escape the gravitational pull of a black hole. Here, pairs of virtual particles are constantly created, one of which falls into the black hole, while the other escapes into space, apparently allowing the black hole to lose mass. This loss of mass is an extremely slow process for large black holes, requiring much longer than the current age of the universe to have an appreciable effect. However, if we project into the distant future, even the most massive black holes will eventually succumb to Hawking radiation, shrinking and fading into nothingness. The final state of this evaporation process is the subject of ongoing theoretical research, with some models predicting a final burst of energy as the black hole's mass approaches zero. This terminal act in the drama of black holes not only marks the end of these cosmic titans, but also heralds a universe in which the very structure of space and time will be devoid of the dramatic interaction of matter and energy that characterizes our current cosmic era. The thermal death of a universe is a theoretical final scenario based on the principles of thermodynamics, in particular the second law, which postulates that entropy or disorder in a closed system tends to increase over time. This profound concept describes a universe in the distant future in which all energy has been evenly distributed and there are no gradients left to fuel entropy-increasing processes. In essence, imagine a cosmos that has reached a state of maximum entropy in which all matter and energy are so evenly distributed that none can be harnessed to do work. In this state of ultimate equilibrium, the stars have stopped shining, black holes have evaporated, and all movement has ceased. The universe becomes a vast expanse of temperature close to absolute zero, where the fundamental forces of nature no longer manifest any discernible action. It is a cold, dark, and lifeless place, devoid of the dramatic cosmic phenomena we observe today. This concept of thermal death is an interpretation of the final destiny of the universe that arises from our understanding of physical laws as we currently know them. It does not paint a picture of a dramatic climax, but of a slow and inexorable slide into a uniform state of inert uniformity, a quiet epilogue to the vibrant cosmic history. The notion of harnessing energy from black holes, those enigmatic titans of the cosmos, may seem relegated to the realm of science fiction, but finds a foothold in current theoretical physics. One such concept is the Penrose process, proposed by physicist Roger Penrose in the 1960s. This process suggests that energy can be extracted from the rotational energy of a black hole by dropping an object into the ergosphere of the black hole, a region outside the event horizon where space-time is dragged by the rotation of the black hole. If executed correctly, a portion of the object can be recovered with more energy than it initially had, effectively extracting energy from the black hole itself. Another intriguing proposal is the idea of a black hole battery, theorized through the manipulation of magnetic fields near a rotating black hole to generate a surprisingly powerful electromagnetic potential. This could, in theory, allow us to harness a black hole as a source of almost immeasurable energy. Although these concepts are based on the laws of physics, the technical feasibility of such feats is beyond our current technological reach, and their understanding involves manipulations of matter and energy at scales and conditions that are currently unimaginable in practical terms. However, the mere contemplation of these ideas expands our imagination and our understanding of energy and serves as a guide for future explorations in both theoretical and practical physics. They lead us to rethink the limits of energy generation and the eternal enigma of black holes in our quest to understand the universe. The limits of human exploration in the cosmos are determined by a confluence of technological, biological, and physical challenges. At the heart of these limitations is the immensity of space. The distances between stars are so colossal that traveling even to the closest star systems within a human lifetime using current propulsion technologies remains a daunting challenge. The speed of light poses a fundamental limit according to Einstein's theory of relativity. No object with mass can reach or exceed this celestial speed limit, making interstellar travel require an incredible amount of time with our current knowledge of physics and technology. Biologically, human beings are not designed to withstand the rigors of long-duration spaceflight. The microgravity environment can have profound effects on the human body, including muscle atrophy, loss of bone density, and exposure to cosmic radiation, which can increase the risk of diseases like cancer. The psychological impact of prolonged isolation and confinement in the vast void of space presents another significant obstacle. Technologically, we are still in the infancy of the development of systems that can maintain human crews for the time necessary to travel beyond our solar system, not to mention the need for propulsion systems to make that trip feasible in a reasonable time frame. The energy requirements for long-distance space travel are monumental, and we have not yet devised a compact, reliable energy source capable of powering such trips. Despite these formidable challenges, the spirit of human exploration and our tireless pursuit of knowledge drive us onward. Advances in robotics, artificial intelligence, and miniaturization may one day allow us to send probes to distant worlds far more efficiently. Advances in physics could reveal new methods of propulsion or even ways to circumvent the cosmic speed limits that currently constrain us. While humanity's journey to the cosmos is currently limited by these factors, our understanding of biology and life support systems will evolve, allowing for longer duration missions with a reduced impact on health. And our history is full of examples of overcoming seemingly insurmountable obstacles, suggesting that these limits may one day be overcome, opening new horizons in our quest to explore the universe.